Hi, my name is Nuno, and I'll be talking about neural electrode surface coatings using carbon nanotubes. We will start with an overview of the world of neurobiology, the state of the art, the project goals, the activities program, the different characterization methods used in this thesis, the results in this discussion, and conclusions and future perspectives. The brain is the most complex organ in the human body, and therefore mankind has tried over the years to develop better tools in order to study our neurons and the way they communicate between them. With over 80 billion neurons, we can see how difficult the task is for the neuroscientists. In the past, scientists could only record the activity of a single neuron through a single wire system, making it impossible to study several neurons at the same time and therefore impossible to retrieve information about the neuron's network. With both recording and simulation occurring simultaneously, we can use exterior impulses to restore hearing, vision, or limb movements, or to help patients with diseases in the nervous system, such as Parkinson's or Alzheimer's. Nowadays, using MEMS, we can use multiple microelectrodes at once. However, a surface coating of the electrodes is needed in order to have low impedance, a large storage capacity, and a high signal-to-noise ratio. Several materials can be used for recording electrodes, such as platinum, gold, or tungsten. These materials are inert, have great mechanical strength, and are highly conductive. Despite this, the electrodes still need materials for surface coating due to the high impedance of gold and platinum at nano and micro scale. Iridium oxide, tungsten oxide, polymers, or carbon nanotubes have been studied over the years as possible coatings, with improvements already proven. Nowadays, there are several types of electrodes in a whole range of applications, such as organic transistors, flexible polymers, optical gold fibers, among others. In this thesis, we aim to produce and characterize different forms of carbon nanotubes surface coatings in order to determine which one ensures a better response over time. Using silicon probes, we will test three combinations: a direct synthesis of carbon nanotubes by chemical vapor deposition, co-electrode deposition of carbon nanotubes in polypyrrole, and another co-electrode deposition of carbon nanotubes and gold. The activities program. We will need to test and evaluate different silicon probes, both morphologically and electrochemically. The silicon probes have different structures and different electrode diameters, and so we need to test them all. Next, using an energy dispersive X-ray spectroscopy, the characterization of the coating solutions is performed. After the solution is being applied to the electrode, using a galvanostat, we proceed to the electrochemical analysis by cyclic voltammetry and electrochemical impedance spectroscopy. And then we test the electrodes in vivo and in vitro using anesthetized rats. Now, the different characterization methods. Cyclic voltammetry is used to analyze the electrode-electrolyte system in a well-defined potential window. It uses three electrodes: reference, counter-electrode, and measurement, and it cycles the electrode's potential and then measures the produced currents. When we apply the potential, electrochemical reactions occur, and the analyte is reduced and oxidized. In this particular case, the CV response is affected by some features, such as geometric area and roughness of the electrodes. In electrochemical impedance spectroscopy, we apply a known voltage or current, and we measure the corresponding electrical impedance. Basically, it gives us the frequency response of the system. If we apply a sinusoidal voltage, we can also obtain the phase angle of the system. It allows us to study both tissue and electrode response and properties, and since it is a non-destructive technique, we can use it without damaging the brain tissue. Scanning electron microscope is an image technique, and it uses a focused beam of high-energy electrons to study the sample. We can obtain topographic information or chemical characterization. A short area is chosen, and a raster scan of electrons is made, allowing resolutions of 1 nanometer. The interaction between the incoming electrons and the sample produces several particles, but only secondary electrons are analyzed by SEM, using a detector. It's an easy-to-use technique, however, it requires the use of vacuum in very small samples. Now the results. Here in these graphics, we can see that the black line corresponds to the uncoded electrode, and the other straight line is the coded one. Polypyrrole and carbon nanotubes, was proven to be the electrode with the higher charge injection limit, and also the one that has the better electrochemical performance. To test the electrodes under mechanical strength tests were made. The electrode formed only by carbon nanotubes is by far the most stable over time compared to the other two. Polypyrrole carbon nanotubes have great electrochemical properties but degrade over time, whereas carbon nanotubes and gold has great mechanical stability but high impedance. All three coatings allow the decrease of the electrode's impedance and improve the signal quality, and they are able to be safely used in the study of the human brain. Here we have a image of the three samples, and we can see how the coatings affect the form of the tip. Now, we obtain three fully operational electrodes with different coatings. Carbon nanotubes formed by CVD proved to be the most reliable electrodes. However, all of them were successful in vivo tests. Carbon nanotubes coating have better signal quality than uncoated ones, and this is a very good thing to use in the future to study the brain. Now, in the future also, we should search, we can and we should search for new coating materials in order to reduce the impedance. Also, if possible, we should study the long-term effects of microelectrodes chronic implants. And again, if possible, in human brains. Thank you for your attention.